We're now going to develop inference procedures for two different populations, and in particular, we are interested in whether or not those populations have different underlying distributions for their individuals xi and yi. We're going to focus on the case of proportions again. So to determine whether or not you have different underlying probability distributions, a good, easy first step is just to check whether or not the proportions are different for each of those populations. Will PA be the same as PB? So that's the motivator here. Let's try to figure out if we can come up with inference procedures for determining whether PA and PB are different. We've got these inference procedures. We know what we should do. We should go ahead and construct confidence intervals and perform hypothesis tests. Now, as always, what we need to do is estimate these population parameters using samples. So we will take a sample from population A. So the sample will have a size of n, and we will use the sample estimate, or the estimator, p hat, and we will estimate the value in particular as the number of successes over n. So we'll say that this is the estimate for sample A, and in sample B, we'll do the same thing. We'll have a sample, it'll be size m, and our estimate here, PB hat, will be the number of successes y over m. Now, just like before, we are going to use a large sample approximation, which essentially allows us to have the central limit theorem kicked in. There is an underlying binomial distribution for each of them, but we are not going to use the exact binomial. So essentially, we are going to ignore the exact binomial n and PA and the exact binomial m and PB for the other one. So that means this, as we talked about in the previous videos, this means that the sample estimator, which is x over n, so the sample estimator for sample A will be approximately normal, and it will be centered on PA, and its sample variance will be given as such. And similarly, the estimator for B will be the number of successes over m, and just like in the previous video, this will be given by these expressions. Now, this is exactly the case as it was before, so there isn't a lot of difference, and I'm just stating the results there. But what is new is that we are going to form a new estimator. We are going to form the estimator PA hat minus PB hat to estimate the difference in these two population proportions. So as always, we need to know information about this estimator, right? What are its properties? What's its mean, etc. Now, from earlier ideas, we know that this is a linear combination of two normal variables. And that means we can put together all of the information we need right away in one step. We'll figure out the mean, we'll figure out the variance, and we'll figure out the distribution itself. So because individually PA and PB are normal, their difference will also be normal. So that tells us what the shape of the distribution will be. The mean is simply the difference in these two individual means, and that was properties of normal distributions we had talked about earlier in the course. And the variance is going to be the appropriately scaled combination. So we'll have 1 squared times the variance of the first plus negative 1 squared into the variance of the second. Now, just to simplify that a little bit, we'll end up with the following result. And again, all of this is dealt with by the rules of probability that we spent so much time on in the beginning portion of the course. Really, inference is where all of this stuff comes together. We now know how to construct the right sampling distributions and get all of the quantitative information we need from here. Now, we are going to build confidence intervals, and we are going to perform hypothesis tests using this distribution. All right, this is the one that we are going to make use of. So everything that we do is going to be based on this result. Now, as before, we are going to ignore the continuity correction in constructing these formulas. It is possible to do them, to include it, but the formulas are not so nice, and the continuity correction becomes less important as the sample size gets larger and larger. So that's why it effectively gets ignored. The test you can do in R to build this stuff will actually allow you to be able to include it if you'd like. But nonetheless, if we want to talk about a confidence interval, remember that we will always have our estimate, PA hat minus PB hat. So these are the observed values. This is our point estimate. And we will stick our arms out by some margin of error. And so the margin of error always works the same. The margin of error is going to be some critical value that is related to the confidence level multiplied by what we call the standard error. The standard error is just the square root of the sample variance. So this is going to end up being PA 1 minus PA hat over N plus PB 1 minus PB over M. Now, as before, if we want to estimate PA and PB, we can't have results in terms of them. So what we do is we replace all the PAs and PBs with their observed values. And their observed values are things you would get from the sample, just like before. And so we would now end up with an expression for a confidence interval for each of these, for the difference in the two here. It would be centered here on the observed point estimate, and then we would add or subtract the margin of error. And so it would be this awful looking formula, but if you've been following along with the ideas of the course, then you know exactly how each of these comes up. And just out of laziness, I'm going to skip writing that square root there. So if we want to do this, we are able to do this. Now, it's kind of a weird thing, but R will actually give you a command to do this confidence interval automatically. So there is an R command for two sample proportions. And it's something called the proportion.test command. I'll give you instructions on how to use it, but what's strange is that it will give you the same results that we get from our formulas for a two-sample problem, but not for a one-sample problem. So in the one-sample problem, the formulas we develop don't have an automated version in R. You could just use the proportion.test command for the one-sample case, but it won't give you the same results as your formulas, which is really annoying. Nonetheless, we'll go from there. So in a hypothesis test, the null hypothesis will typically always be that there is no difference in the values. So that PA equals PB. The alternative is going to be one of PA less than PB, PA greater than PB, and PA not equal to PB. And you would have to decide on the correct one depending on your particular problem. And so now the hypothesis test is the same sort of form. What you need to do is you need to construct a sample statistic to get some evidence. So your sample is going to provide you with your estimators P hat A and PB hat. And what you need to do is form your sample statistic. Now we know that the hypothesized value here is going to be PA equals PB, or another way of putting it is that PA minus PB is 0. So this piece of information sets the center of the sampling distribution right there. So remember, this is PA hat minus PB hat, the functions themselves. And the null hypothesis will always give us a 0 and set the center. And when we take a sample, we'll get a PA hat, PB hat, the little lowercase ones, and this is going to give us an observed value, PA hat minus PB hat. There'll be some tail area that we need to compute. Now, as always, we want to standardize this and turn this into a standard normal problem. So this would be on the z-axis. Now, there's one complication here when we standardize this. So if we take our z statistic, we will always have the observed sample statistic minus the hypothesized one. And the hypothesized one here is going to be 0, because that's what our value is saying. And then what we need to do is divide by the standard error. Now, the standard error makes use of hypothesized values. The issue is we don't have individual hypothesized values. We only have that PA equals PB. And so if PA equals PB, let's just call it P for now. If those two are true, then this sample standard error has a common factor that you could pull out. It'll have a common factor of P, 1 minus P, and we'll have 1 over N plus 1 over M. But the headache is, what is this thing P? You could pick one of the two sample proportions to do it, but what we do instead is we construct what's called a pooled estimate. So essentially, it's a linear combination of the two sample averages, and they're weighted by the size of each sample. So if one sample is much, much larger than the other one, then that sample proportion will get more weight and vice versa. It simplifies down to just adding the number of successes divided by the sum of the sample sizes. So we'll call this P hat. So this P hat is our estimator for the actual proportion. So at the end of the day, the statistic that we compute is PA hat minus PB hat, subtract 0, and we will put in this pooled estimator as such. So there are a lot of formulas, and yes, you can have your textbook, but all of this stuff will be available and built into R. So once again, this is automatically done in proportion.test in R. So it makes life very, very easy. Now, I have posted a sample file of R code that will allow us to compute these things as needed. Now, I'm going to look at an example, and the example that I'm going to look at is the smoking example here that's on the PDF file. So essentially, we are comparing two different populations. The population A will be the population of smokers who are just using the patch. And this is the proportion that we're interested in. And the second one will be the patch plus the drug. And so we want to compare and ask, is there a difference in PA versus PB? Now in part A, we are asked to build a 99% confidence interval. So a 99% confidence interval for the difference, you have to be clear here of what it is that you're trying to compute. So we are going to take a sample, which we have been given information, and we will subtract margin of error, and same thing happens over here. We'll get our sample estimate and we'll add our margin of error. The margin of error needs a critical value times the standard error. Now the standard error is that big awful thing in the square root. I've provided just a way for you to code it in R very simply. This critical value comes from the standard normal distribution. And it says, okay, if I want a 99% confidence interval, then this area has to be 0.99. That means there's 1% to share in each tail. So this is 0.005. And that means that I can determine this Z critical value using R. I will use the Q norm function. And I'll put 0.995, 0, and 1. And this will get me the correct value that I need. And so you can print that out in R as you need. And then once you've got this value, you can construct your confidence interval from above. Now, if you build this, you can either use the proportion.test command, or you can build it out manually. So in the code that I've provided for you, I have given you both of them. Now, both of them will return the same result. In this case, we are fortunate that R gives you the same value for its built-in test, which makes it really frustrating that it doesn't do it for the one sample proportion. But either way, we end up getting the following result, that the sample, the difference in the two of them is about 0.2908 PA minus PB up to negative 0.0915. Now, this tells you again, patch, subtract patch plus drug, the difference in the proportions. Since 0 is not in this interval, we are confident that there is a difference, right? This interval gives you the plausible range of values for PA and PB. If 0 isn't in there, if they're all the same sign like they are here, that means you are confident that there is, in fact, some difference between the two of them. Now, another way to frame this would be through a hypothesis test. So if you wanted to frame this as a hypothesis test, you would say that the null hypothesis would be that the difference of these two is 0. And the alternative, if we read through the question here, is that we are supposing that more people quit using the patch and the drug. So that means we suspect that PA is less than PB. And that's going to be important because when we use the alternative command here, we are going to be following a less test. Now, the sample evidence is always the same. It provides us with a PA hat and a PB hat. And what we do is we can form the Z statistic. And the Z statistic is always going to be the same. PA hat minus PB hat. This difference here is always going to provide us with the 0. And then we will divide by the standard error. Now, the standard error in this particular problem uses the pooled estimate. So you could compute it manually, and you would come up with a result, or you could compute it in R. Now, to compute it in R, what you need to do is build a vector that stores all of your sample successes and another vector that stores all of your sample sizes. Once you do that, you have to tell R that you do not want to use the continuity correction. So you'd have to set this command correction equals false. And again, I've provided the code for you there. Either way, whether you do it manually or whether you do it with the automated version in R, you're going to come up with a p-value. So the p-value in this particular case is going to be 7.16 times 10 to the minus 7. This is very, very, very tiny. And this gives us strong evidence to reject the null hypothesis. So the idea here is that the tools we are using follow the same philosophical idea. You build them the same way. All that's happening is that the details change. If you want to do things manually, you can use R as a calculator and do that. You're going to need certain results. I provided a code that will allow you to compute all of those easily. But what's even better is that R will automate all of this stuff for you for two-sample proportion.